Welcome to the Maitrix error correcting demonstration. If you're watching this video, you probably found our page. I'm going to scroll down and now start the demonstration PowerPoint. The demonstration PowerPoint will describe the block diagram of our error correcting demonstration. If we look to the left in purple, we have a data A memory and a data B memory. These are ROMs, or actually RAMs in this case, that store 32-point fixed point binary. This binary are randomly chosen in this demonstration by the NEOS processor. It is signed values. That data is then sent into the blue box you see called forward convert. In the forward convert process, binary data is converted into RNS data. The RNS data is then sent into our multiply and accumulate unit. Notice that this is the unit that is overclocked. It is highlighted in light blue. The overclocked region can be controlled by a high-speed variable clock shown in brown just to the bottom of the highlighted blue area. The overclocked region can accept data from dual clock FIFOs, and once the multiply and accumulate process is complete, can send the completed product summation to the dual clock FIFO on the right of the light blue area. Once these answers have been accumulated into the answer dual clock FIFO, they can then be sent to an error correction unit shown in red. The error correction unit is capable of correcting any single digit error in the multiply and accumulate answer, which are dot products. After the error correction unit, the answer is then sent to a normalized unit, which is optional in our demonstration. However, the normalized unit converts the unnormalized product summation into a normalized residue product. That means that this answer could be then sent back into the input of the multiply accumulate. The last block in blue in the far right is the reverse convert. The dot products still in the residue number format are then converted back to the binary format with the reverse convert block. The resulting binary data is then stored in a result data FIFO, and the NEOS 2 CPU, shown in orange or tan, can then read the data and report it to the screen. Also note that there's an error code FIFO that also records the status of the dot products as they had been tracked through the error correction unit. This can also be read by the NEOS 2 CPU and reported to us on the screen. Okay, let's get started real quick and show the actual demonstration. This is a live demonstration of the error correction demonstration. Notice that we have 16 dot products, or essentially 16 product summations, and they're changing. Each one of the product summations is a result of 16 products and that have been summed. Note that the result is signed, so as these numbers go by, some of them are positive and some of them are negative. Now, also note in the upper top red, the frequency set here is 215 megahertz. I'm going to highlight that here. This is the frequency at which the product accumulator is running. Note that the other parts of the product summation or the error correcting pipeline are basically not being overclocked. So this is the safe clock region, and the safe clock region allows us to clock our error correction unit and our normalize and our converters at the correct clock rate. It's only the multiply and accumulate that's actually going to be overclocked. Okay. All right. Another thing that you should note is when you're looking at this demonstration is you can also refer to our website and our GitHub site. And at our GitHub site, we have the repository for this project here at the Error Correcting Arithmetic FPGA demo. And in this repository, you can also pull out the instructions for this demonstration. Now, real quickly, I'm just going to move to the end. I've set this up already, and I'm going to move to the end where we have the hotkeys. So some available hotkeys in this program are, if you press a C character, you'll clear the screen. If you hit the D screen, you're going to change the numeric format. If you hit the R, you're going to clear the counters, which I'll show in a second. You can pause the demo, switch the mode. There's up to 4 modes available. Can change the clock source, and we can change the value in particular modes. Okay. So if we go back to the demonstration, I'm going to go ahead and enable the camera now. And so you should be able to see the actual apparatus actually running. And note that I have a function generator connected to the product summation demonstration. Now right now we're running at 215 megahertz and everything looks pretty good. You can see at the bottom we have OK, it's about 33,000 runs, 100% OK. There were no corrected products summations, and there are none that were uncorrected. Now before I do that, I want to really quickly point out one quick thing here. And this right here is just a screenshot of the Quartus Compile of this particular project. And if you note, the safe clock is potentially running up to 165 megahertz, whereas the F clock, the fast clock, and that's our multiplier accumulator, the Quartus is reporting that the top speed of this would be 256 megahertz, which really isn't too bad when you consider the Intel specification for this part. Now we're using a -C4 performance Stratix or Arria-10 FPGA. And so the Arria-10 FPGA is a -C4 speed grade. Notice that the independent 18 by 18 multiplication is rated at 370 megahertz. Okay, so if we refer back to our compiling report, we see that our DSP multipliers, in the case of the multiply accumulate unit, are running at 256 megahertz top speed according to the reports of the Quartus timing analysis. Okay, so it's important to understand that. Our reports say that we can run up to about 250 megahertz, and the top speed of the DSP block is 370 megahertz. Okay. All right, returning back to our product accumulation pipeline. Now I'll go ahead and put up our error correction demonstration. We've got the camera on. And now what I'm going to go ahead and do, as random numbers are being sent to the product accumulator pipeline, I am going to go ahead and increase the frequency. So as you can see, I'm beginning to increase the frequency, and if you watch the frequency counter in red on the top of the screen, you'll notice that it's going to be increasing. And the reason why it's going to be increasing is because I'm increasing this function generator here. Now interestingly, as I increase, now we're getting past what the rated frequency was from the Quartus report. We're now at 263 megahertz, and this is greater than what was reported, right? The 256 megahertz. So we're past 256 megahertz, and because everything is shown in green, we don't have any arithmetic errors in our product summations. Now as I increase the frequency, you'll notice that we're now at 269 megahertz. And by the way, this is the internal frequency that's running. It's not the frequency I'm sending in by this frequency generator. We're using a PLL to multiply this up here. But the demonstration is reporting the internal frequency with its own circuit. And so this is what we're at right now. So now we're about 300 megahertz. Now keep in mind, according to the Intel specifications for the Arria-10, the DSP blocks for this particular part should be capable of running up to 370 megahertz. Now, keep in mind too that this is 32.32-bit signed arithmetic. This means that you have 32.32-bit products being multiplied and then being summed in an accumulator, and this is happening in a pipelined digital structure is running at this speed. So you're basically getting one multiply and one accumulate every clock cycle, and we are now running at 323 megahertz. Okay, as I speed up, we'll notice that we're now at about 350 megahertz. Notice that the RNS processing is extremely resilient to errors on its own. Despite the fact that the Quartus report is showing that we're about 100 megahertz overclocking as it stands right now, and the product summations are still correct. Well, we just got one that was corrected, and that just came in on yellow. Now we're going to increase the clock frequency here, and we're going to see more of these errors occur. Keep in mind that we're in an unstable region right now, so it's difficult to say exactly what's happening because, well, we're overclocking this circuit. Now, if we begin to overclock, our error correcting unit is going to begin to try to correct units or results that have an incorrect digit, and those will show up as yellow. If the error correction unit is not capable of correcting the product summation, that value will be shown in red. So let me increase the frequency and you will see this effect. Also note on the right, I have corrected RNS digits, and they're kind of showing up. And let me go ahead and move this over just a little bit here for you. Okay. So the corrected digits are showing up on to the right of the terminal. And the corrected digits are being detected by the error correction unit. So whenever you see a value in yellow, that value is still correct, it's just been corrected. If you see a value show up in red, that value is not correct, and the error correction unit was not able to correct the arithmetic. And generally the reason for that is there's more than one digit that was incorrect in that calculation. And in this particular system we have 10 RNS digits, and that's why you see the corrected RNS digits 0 through 9, and we're showing that. Now, we're already running at the speed of the DSP block. That's according to the Intel specification that I noted earlier. Let me go ahead and remind you. Here it is. An independent 18 by 18 multiplication, its top speed is 370 megahertz on the dash C4 rated part. And that's top speed. You're not expecting to actually reach that speed. But we're already at that speed. And as you can see, most of our calculations are correct. And even the ones that aren't correct, we know that they're not correct. That's a very important point as well. We're going to go ahead and now move the frequency a little bit slower. And we're going to now try to begin to increase the frequency well beyond the rated frequency of this design, and also well beyond the frequency of the DSP's top rating. Okay, at 381 megahertz, you can see we're correcting quite a bit of errors here. And if you were to let this go, now you just saw a bunch of red values go by. Yes, this is unstable. Sometimes clocking errors propagate, and once a clocking error occurs, then it continues to propagate until the system resets. That's probably a good thing to note, is that we are doing bursts here, and so we're giving the product summation unit many times to continue to run again and again and again. So we're at 380 megahertz, and I'll go ahead and increase it a little bit higher here. Okay, so we're at 390 megahertz. So we're doing 32.32 signed fixed point arithmetic at 390 megahertz on an Arria-5. Without the error correction, we wouldn't stand a chance, and without the modular arithmetic, we wouldn't stand a chance. So it's very difficult to get binary arithmetic to perform at these levels, at this resolution. Now keep in mind that we can extend the resolution of this technology and go for much greater numeric accuracy if we want, or we can reduce the numerical accuracy. And we'll just go ahead and push it on right on up to 400 megahertz. So you can see at 400 megahertz we're going to be getting much more errors, so you're going to see more red in this display. Now if you let this sit for a while, then you can get basically an average statistic, or in one of the menu items in the demonstration allows us to reset the counter by hitting R. So let me do that real quick. If I hit R, I'll reset the counters, and now we can get a little bit better idea of what the actual percentage of errors versus the percentage of correct versus the percent of values that are okay. And that's being shown at the bottom there. So okay is about 30%, and those were values that still came through that didn't need correction because they were still detected as correct, even at 400 megahertz. Now in yellow is the corrected. That's the highest percentage. We're at over 50% of the arithmetic results are being corrected right now. And you can get an idea that the digit 1 is very weak. It's not the only digit that's failing by any means, but it's obviously the slowest one. And then on the non-corrected thing, we're getting about 14% non-corrected values here. And this part of the curve is very similar to this part of the demonstration right here. If you look at this curve, the bottom is increasing frequency. The green is the number of arithmetic results that did not need correction. It drops off as frequency goes up. The blue is the number of values that were corrected. It peaks at about 396. And then it begins to drop. And here is your not corrected. Those begin to accelerate as you finally get up into the very extreme frequencies. And so we can actually demonstrate that right now. But this is what this curve means. And basically, as you can see, we're at 400 megahertz right now, and these are the ratios that the curve is really looking at. So if we if we continue to increase, we're going to just see that the non-corrected errors are going to begin to increase. And again, if we reset our counters, yes, we can see right away that our non-corrected errors are about 30%, our OK is about 18%, and our correction is about still over 50%. So this is quite an amazing technology, what we're able to do here. We'll go ahead and just run it a little bit farther just for fun, in case you're still hanging in there. This is 420 megahertz. You don't see too much green there, but every once in a while the residue is so resilient to errors that it'll still process something correctly. Now there were some zeros that went by that are green, so this circuit does not detect the fault zero. And this circuit also is not a perfect circuit. There are some glitches even with the with the construction of this particular demonstration. But it does clearly show the power of the error correction technology. Again, we're at 420 megahertz. If we just make a quick reset of the counters, we're still getting about 50% corrected results. And there are about 37% that are not corrected. And we'll just go up a little bit higher. And we're at about 426 megahertz. And again, we can go ahead and reset our counters. And now we see that the non-corrected results over 50% and the corrected is under 50%. Interestingly, you still have about 5% of values that come through that are just correct. And we're operating at 427 megahertz. It's well in excess of what the rated Quartus was on this. So that's what it looks like. Again, we'll just step it up a little bit farther until it just finally saturates. Interesting, we can get an error. Even still, a corrected result at 440 megahertz. Not the zeros, but every once in a while you may see one come in that was corrected. Right there. So maybe only 3% of the results have been corrected, and now the majority are incorrect. Again, if we back down the frequency, continue to back down the frequency, now we're getting back into the realm of where the calculations are correct. Okay. Some of the other interesting parts of this demo is that the demonstration does provide for to switch the mode. So we have some different modes that the thing can run at, as well as the different clock sources. So there's some internal clock sources that you can choose using the F key. But the mode is an interesting one as well. So if we come in here, we can hit M, go to mode 2. Notice the mode is right under the red bar here. So we have the frequency configuration is at setting 3. The mode is at setting 2. And what's interesting about mode 2 is that it just keeps the same data going through. And it's an interesting test because if you're wondering, hey, does this really work? This is what the data shows to be when it's green, when it's correct. And as we crank up the frequency here and correct it, and I'll go ahead and hit reset so I can reset this counters here. And as I go ahead and increase the frequency to the point where corrections begin, then you'll notice that those corrections are the same number. If I back off the frequency, those numbers never changed. And that's a sure indication that my corrections are working. When I change the frequency, you'll see you get a rash of errors because we're swiftly changing the input frequency, and the PLL is obviously losing lock. And obviously our input signal generator may not be all that stable as well. So there's plenty of sources for clocking errors here in this demonstration. Okay. And then we can also change, because interesting about this particular mode is because the value remains static, we can see the errors remain static. And so we're really seeing the effects of clocking due to delays in the particular circuit in these areas. But it's also data dependent. So if we hit V for value, we can change up the value. And by changing up the values, we can get different results and different types of errors and different digits. So again, we're running at about 377 megahertz. And each time I change up the values on this. And so there's an interesting one. There's an error. So in that particular product summation, there's more than one digit that's an error. This particular error correcting demonstration is a single digit error correcting capability. All right. Well, that pretty much concludes this demonstration, and we thank you for watching. And we're looking forward for more demonstrations in the future. Thank you.